Hello, hello, welcome. This is the Chemistry Cowboy, bringing you back to physical chemistry. Chapter 9. We've already looked at real gases and ideal gases. Now we're going to look at ideal and real solutions. So, it's starting to get hard. And you said, starting to get hard? Yes. It will start to get hard as we start to look at how real solutions act differently from ideal solutions. But we'll try to take this as slow and steady as we can. So, first thing we got to do is remind ourselves how we dealt with this in chapter and general chemistry 2. We looked at colligative properties. So this is, we looked at the chemistry of solutions. So we want to look at what really happens when I dissolve this salt in water. We only scratched the surface during general chemistry. So when we looked at the colligative properties, and even then, we made a lot of convenient assumptions that sometimes leads to some errors. One of the main ones is the idea of a formation of an ideal solution. So first, what is an ideal solution? Well, ideal gas, we make the assumption that no atoms interact. But we can't make the same assumption for a solution. A solution, by nature, all molecules will interact. But what makes an ideal solution is that we say all molecules interact identically. Just like we say in an ideal gas, all molecules interact identically in that they don't interact at all. On a ideal solution, all molecules interact identically. Like it doesn't matter whether I have A and B, whether A and A interacting or B and B, those are the same as A interacting with B. So we don't say, oh, this one's water and this one's oil, and we have to consider what fractional interactions. It just, those don't interact. But if I say, like, how does water interact with alcohol? Well, water is going to be slightly more polar and slightly more hydrogen bonding than alcohol. But we just wave our hands and say, yeah, it mixes uniformly, and there's uniform reactions throughout. So, as I said, this is rarely the case. For this to be true, the two molecules must be similar in size, shape, and chemical properties for them to alcohol to alcohol be identical with water to water. I mean, we can get pretty close like that with methanol and water, but it's not going to be perfect. It's not going to be ideal. You just look at Raoult's law. So imagine a solution of benzene in a jar. At equilibrium, there's a constant vapor pressure created by the evaporation and condensation of benzene within that closed container. There's going to be some amount of benzene in gas phase, some amount of benzene in liquid phase. And that's going to be true at a given pressure and temperature. Now, if I consider it a similar jar with benzene and toluene, this reaction will be used often because benzene and toluene form an almost ideal solution. They are very, very similar, except for the whole great difference in boiling point brought on by toluene's methyl group. Other than that, they are all van der Waals, and they have a lot of pi cloud interactions. Now, the vapor pressure of each gas is reduced due to the interactions by and the pressure from the other's vapor pressure, such that Raoult's law states that the pressure of one gas is equal to the mole fraction of that gas times the pure vapor pressure. So if the vapor pressure of benzene was, say, hypothetically 5 torr, and benzene makes up 50% of the gas, then the vapor pressure of benzene is actually going to be reduced to 2.5 torr. So vapor pressure, it's just of a gas I, mole fraction of I times the pure vapor pressure. So that is a statement of Raoult's law. So if Raoult's law is true for ideal solutions, well, this law is true for all ideal solutions, but it begins to fail when we get to real solutions. It's a limiting, we call Raoult's law a limiting law, in that for real solutions, it only remains accurate when the solution becomes highly dilute. So as it becomes more and more and more dilute in one of those gases, one of those liquids, it still remains accurate. We have an asymptotic effect. As it gets more and more concentrated and they're more on equal basis, suddenly now there becomes larger and larger degrees of error. So that's what it means to be a limiting law, that as it approaches the limit, it becomes accurate. But then as it moves away from the limit, it's going to be less and less accurate. So a few other notes. The substance in greater quantity would be considered the solvent. The substance in lesser quantity would be considered the solute. And for a binary ideal solution, we could say Raoult's law says that the total pressure, which would be P1 plus P2, is equal to mole fraction of 1 times the P star 1 plus a mole fraction of 2 times P star 2. And that at any pressure above the P total, we have no vapor will form. So if the total vapor pressure is, and say 12 torr, and I have an external pressure of 15 torr, we're not going to see any vaporization. So we look a lot of binary solutions. So let's get back to our good friend chemical potential and how this relates to solution. So when the solution is at equilibrium, remember we have some amount of gas, some amount of vapor, or some amount of gas and some amount of liquid. To be at equilibrium, the two phases must have the same chemical potential. So we can state that the chemical potential of the solution is equal to the chemical potential of the vapor. And then we can say from chapter 6 that the chemical potential of the vapor is equal to the ideal chemical, well, the standard chemical potential, mu naught, plus RT ln pressure over P naught, 1 bar. So we can say the vapor pressure is the standard plus RT ln P. And so this must also equal our chemical potential of solution. So what that means is now we're saying mu star is equal to the chemical potential naught plus RT ln P star. So if this is our pure solution, our pure vapor pressure is equal to RT ln P star. And this is our vapor pressure at non-pure. We can subtract these two to get us that the chemical potential of our solution is the mu star plus RT ln P1 Pi over P star. So the pressure over pressure star, which is going to be mole fraction. P over P total. P over P pure, because remember we said that what? Annotate real quick. Said that Pi equals mole fraction I P star. So if I subtract those two together, we say RT ln Pi minus RT ln P star I. You can absorb those together to get us this. So So, okay. So we say essentially the chemical potential of solution is equal to the chemical potential of pure plus RT ln mole fraction, owing to the fact that this. So for an ideal solution, the chemical potential, so this is always going to be a fractional number, and the natural log of a fractional number is always going to be negative, meaning that for an ideal solution, the chemical potential will always be lower when a solution mixes. So there's always going to be, the solution is going to be always lower than the pure solvent. So pure solvent plus the mixing, active mixing is going to be potential of our solution. So remember, solutions naturally want to mix because we want to store as much chemical potential as possible. So we calculated in a couple chapters ago the spontaneity of mixing. Let's see, the chemical potential can be substituted for the Gibbs energy, the molar Gibbs energy. Good time to bring up mixing again. So we said the Gibbs of mixing was equal to nRT, the sum of mole fraction times the natural log of the mole fraction. We said the delta S of mixing was just negative nR, sum of mole fraction times the natural log of mole fraction. So we're able to calculate those just fine. The Gibbs of this, and to add up all the different components. Now, we also should have considered the volume and enthalpy change when mixing are done, since we're dealing with liquids. So volume of mixing would be, how does Gibbs of mixing change with pressure? Well, it should be zero. It should be zero, an ideal one. And delta, the volume of mixing should have no net change. And the delta H of mixing should have been the delta G plus T delta S. So that should have been zero as well. So for an ideal solution, enthalpy and volume do not increase as a result of mixing. If I mix toluene and benzene, the volume of when I mix those two together, if I add 5 mils of this to 5 mils of that, I should have a total of 10 mils. And if I mix 5 mils of them with 5 mils of that, I should be the same temperature. There would be no heat exchange as that occurs. So that's an ideal solution. For a non-ideal solution, you're going to see a change here, and we're going to deal with that. So that's not always the case. So up until now, we've looked at mixtures in only one phase. So either we've all said everything's a gas, everything's a liquid. We've never dealt with two phases. But in this chapter, we're going to look at two-phase binary mixtures. We experience a situation where the ratio in solution above the solution is different. Where if I might have 50% of the liquid being benzene and 50% being toluene, but then in the gas phase, I might have 75% toluene and 25% benzene. So depending on how much I started with, we're going to have more in one phase than in the other. In this case, we will use X as a mole fraction and in the solution, and Y as a gas phase mole fraction. So we have a separate mole fraction depending on whether we look at the liquid phase or the gas phase. Now the I is just saying for each individual molecule, so depending on how many molecules we have. So to handle this, we need to think of some useful equations. We can write Y as so we can write Y sub I with the minimum number of variables. So the first one are Dalton's law of partial pressures, that P total equals P1 plus P2. And P1 is equal to the mole fraction of 1 times P star 1. Now, rather than having mole fraction 2, we can say not mole fraction 1. Everything that is not mole fraction 1 has to be mole fraction 2. Because if I have two gases and mole fraction 1 is 70%, then by definition, mole fraction 2 must be 100 minus 70, or 30%. So we can say 1 minus x of 1. And so we can remove a secondary variable. Now, as we evaluate that, we get that the P total is now P2 star plus P1 minus P2 star x sub 1. Now, since P star is a constant for a molecule, the total pressure only depends on the mole fraction. And we will attempt to treat our Y in the same way. Well, Y, the mole fraction is going to be P1 divided by the P total. And if P1 is mole fraction 1 over P1 times P1 star, and P total is P2 over P1 minus P2 x1, we can rearrange this to say that x1 is equal to, essentially, get x1 over here. So that x1 is equal to y1 P2 plus P2 star over P1 star plus P2 star minus P1 star y1. Plugging this back in to P total, we can essentially say P total is P1 star times P2 star all over P1 star plus P2 star minus P1 star y1. So the pressure total is equal to a bunch of constants and the mole fraction in the gas phase. Finally, rearranging for Y, we essentially have Y1 is P1 star P total minus P1 star P2 star. P total minus P1 star minus P2 star. So constant, total pressure, constant, total pressure, constant. Basically, if I know the total pressure and I know what two components I have, I can figure out what is the mole fraction. And that is actually pretty convenient. I know this is a hot mess of equations, but it's a really convenient way to find out what is the mole fraction in the vapor phase based on what pressure are we experiencing in the vapor phase. Finally, if we have X and Y, it leads us to, of course, Z, the average mole composition. Z is the composition of a molecule both in the gas and liquid phase. So it's essentially looking at the total moles of benzene divided by the total moles of everything involved. The moles in the liquid, moles in the vapor phase. Moles in liquid of everything, moles in the vapor phase of everything. So we'll be able to look at what is the total percentage of benzene in all things. So why is all this important? So we're going to start plotting this shit. We won't actually plot it, but it will be plotted and be considered. So we can plot the effect on liquid or vapor mole fraction on vapor pressure. So basically, remember that when we're above that P total, we're not going to have any vapor pressure. So pressure above that is going to be everything's liquid. Any pressure below that, we're going to start to have liquid and vapor phase. That's based on that Raoult's law. We said P total is P1, X1, P1 star, and plus X2, P2 star. Well, we can also plot the vapor phase. Once we get to a certain point, that anything pressure below that and everything has evaporated. anything above that becomes liquid and vapor phase. So we can look at how mole fraction depends on, and pressure depends on liquid versus liquid vapor, and how mole fraction in the gas phase versus pressure would determine whether we have liquid or vapor. Liquid and vapor, or liquid or just vapor. So this one's looking at mole fraction X versus pressure, where everything above that is liquid, everything below is vapor, liquid. And mole fraction Y versus pressure, where everything above that is liquid and vapor, and everything below that is vapor. Now we're going to put those together to get a PZ diagram. PZ diagram. So this is where we need the Z, because Z is the total mole fraction, not just the liquid or not just the vapor of benzene. It's the total moles of benzene. How does the total moles of benzene affect this? So we could turn this into the total moles of toluene, or just be going the other way. But we're only going to look at really one mole fraction at a time. So we can combine these two, we get the PZ diagram. This is far more informative than the other thing. It allows us a pure liquid phase to be connected to a pure vapor phase by these horizontal lines. So we can say, like, looking at this pressure, we can go from one way to the other. So this pressure, if I have this much benzene, it's all liquid. If I have this much benzene, well, it's all vapor, and anywhere in between. The center space between where these two graphs coincide is our vapor-liquid phase. Now, there's a bit of math in this graph, but we can calculate essentially the amount of a molecule in each phase in this graph. So the next example, we're going to look at point B, this point where we have some amount of liquid, some amount of vapor, and so say we have a high pressure, we go low pressure, we could say 22222 at this amount of benzene and total amounts of benzene. Pressure, you see some vaporize, and then finally it's all vapor as we get low enough. So we're going to look at point B in here. Okay, this is where we get the lever rule. The lever rule says that connecting liquid phases, well, essentially the point B, which connects the liquid phase L to the vapor phase V. So the amount of liquid at point B is equal to the total mole fraction of benzene minus the mole fraction of benzene in the solution phase. Which is essentially the total moles of benzene total over total moles minus the total moles of liquid over the total moles of benzene liquid over total moles liquid. The amount of the vapor phase for at point B is going to be the opposite thing. So Y sub B minus C sub B. So if we subtract the two, so this is just the definition of each guy. We subtract the two. Let's say. Yeah. Okay. Now, in order to subtract the two, we are essentially saying we're multiplying by total L sub B, the amount of liquid, by the total moles of liquid to get these into the same units, so they can subtract better. That would be the total moles of vapor. We would get essentially that the L sub B and total moles of liquid, V sub B, total moles of vapor, is that comes out. So let's add that. And liquid. So N liquid V total, that becomes N total V. So you get N total V. Okay, so let's just look at the lever roll. So let's note take this up. Okay, let me just draw on here. So okay, N total of liquid plus N total of vapor. That is equal to N total. So this part cancels out that part. So what we have left is N total of B. Well, N total of Bu is equal to the amount total moles of liquid and the total moles of vapor of B. So that's N total and that's N total, and those cancel out each other. So saying if I subtract the amount of liquid times the total moles of liquid at point B minus the amount of vapor times the total moles of vapor, I'd say the net change is 0. And because that's 0, I can solve for the amount of liquid versus amount of vapor of B at B. So I essentially say that I move that to the other side and I cross multiply. So I have what? LB and equals VB and vapor. So that's where we get the N total liquid over N total vapor equals the LB over BB. Well, VB over LB. So, or essentially put the total moles of liquid times the mole fraction of benzene minus. So this is saying how much benzene. It's a way to conveniently look at how much benzene is in the liquid phase or the vapor phase at any given time based on where this is at in the point. So N total liquid is equal times the the total amount of benzene minus the mole fraction of benzene in the liquid phase, and total vapor times the mole fraction in the gas phase minus the total amount of benzene. This is all a hot mess of confusion, but so hopefully this next slide will help us understand this, because we're going to actually work through a problem. So ideal solution is created by mixing 4 moles of methanol and 2 moles of ethanol. They're pretty similar. The total vapor pressure is 95. What is the composition of each phase and the composition with respect to ethanol? What is the total of each phase and the composition? So here I give you the vapor pressures of each guy. So first things first. What is the Z of ethanol? We have 4 moles of methanol and 2 moles of ethanol. So Z, oh. I note the crap out of here. So start off Z of ethanol. Ethanol is going to be what? 2 divided by 6, or essentially 1/3. I'm going to say 0.333. So that's going to be our. Now the total pressure is 95. So what is the mole fraction of ethanol? We're going to think of this in respect to ethanol, even though ethanol would be the solute. So P total, 95, equals methanol would be our P2, 127, plus what? 59 minus 127. So let's do that. So 95 minus 127 is negative 32. Negative 32 equals 59 minus 127 is negative 68 extra ethanol. So negative 32 divided by 68, negative 68 is the amount of ethanol in the liquid phase is 0.47, we'll say 1. So there's a lot of ethanol in the liquid phase. There's the great, well, considering ethanol makes up only a third of the total amount of the solution, it is almost half of the liquid. Now let's look at the mole fraction of ethanol in the vapor phase. So we got 59 times 95 minus 59 times 127 all over 95 59 minus 127. The top part. The top part is negative 1,888. The bottom part is negative 6460. 6460 equal to, so the amount of ethanol in the vapor phase is 2.292. So that should tell us everything about the that should tell us everything about our how much of this we have in the of each phase. So right there, that's our mole fraction of ethanol in each phase. But that doesn't tell us necessarily how much total liquid we have, how much total vapor. So the last one is, so let's go ahead and keep working. Let's see. And I'd have to think about the end total liquid. We don't quite got that yet. End total liquid is equal to what times the mole fraction of 0.333 minus our 0.471 must equal the end total vapor times 0.292 minus 0.333. Okay, I remember how to do this now. So that's 0.333 minus 0.471 gives us negative 0.138, and 0.292 minus 0.333 gives us negative 0.041. So from here, we can relate the total moles of liquid to the total moles of vapor by the relationship. So I'm going to divide 0.138 divided by 0.041 to give us that the total moles of vapor, and vapor is equal to 3.36, we'll say 6, the total moles of liquid. And okay, with that in mind, the total moles that we can have is 6. The total moles we can have is 6. So if the vapor is 3.366 times the amount of liquid, we're going to take 6 divided by 4.366 to get how much liquid. And so the total amount of liquid, the N liquid right here, N liquid is going to be, we have 1.374 moles of liquid, and we have 4.626 moles of vapor. Of that 1.374, remember, 0.471% of that is ethanol. So like, of the 2 moles of ethanol we have, 0.647 moles of ethanol are in the liquid phase, and the rest is in the vapor phase. Of the 4 moles of methanol, we have 0.726 moles or 727 moles of ethanol in the liquid phase. So using these 3 equations and these numbers, we essentially calculated, what is the mole fraction of ethanol in each phase, and how many moles of each guy are in each phase. So we have the greater portion of all the moles are in the vapor phase. So a lot of these guys vaporized. And a greater portion of the vapor phase is methanol. But we do have a somewhat significant portion of ethanol in the vapor phase. So it's nothing to scoff at. So, but that is what essentially we are doing. So, I mean, that's a hot mess by itself, but taking each part into account, you can find out exactly what's going on in this ideal solution. So, a few more slides and then we'll stop. But so another diagram we can look at is how temperature affects the Z. Previously, we're just looking at a PZ, a pressure diagram. How can we change the temperature and affect the mole fraction? So we're converting this to a TZ. So you're looking at T on the x-axis versus this. And we can use the lever rule as part of what's called fractional distillation. That at a certain temperature and a certain mole fraction, so we're going to be moving our way over from liquid to vapor fraction and purifying this. And as we move our way down, our temperature is going to decrease, move down. And it's going to keep on going down, and we're going to keep purifying to get more and more concentrated in the liquid, more and more concentrated in the vapor. So using a mixture of benzene and toluene, where relatively pure boiling benzene boils at 350 well, we have 353 and 383, respectively. Benzene and toluene boils at a completely different temperature. The solution essentially is boiled at a temperature A, and we move our way across. It's boiling. We're allowing it to go to a vapor phase. We're right here. And when we go to the vapor phase, a portion of the vapor escapes across that tie line to point B. So we're essentially, we boil these guys because they have a different boiling point. We lose a certain amount of one guy versus the other guy. And so we get, then we allow it to cool. As the solution can then be cooled to point C. So what hasn't completely been lost in the vapor phase now moves down. So we allow it to condense, but of course then it boils again. As it boils again, we move our way to point D, allowing more vapor to escape, so more of the benzene is left behind. So the amount of benzene in solution is now going up and up and up as we allow it to boil at the lower and lower point until we get down to a point where we get to pure benzene, which boils at 355. So essentially, by doing a series of boiling, we can get pure or nearly pure benzene. Of course, the main limitation of this is what's your time and how many steps are you willing to take. You see, fractional distillation, we heat it up, you get some amount of benzene, some amount of toluene, and mostly benzene down here. And then you heat this up, and it's like some amount of benzene, some amount of toluene, but it's now in more and more pure as the toluene gets further and further up until you have like essentially just one pure product. And of course, the vapor phase, and you can say, who the hell cares about the stuff at the very top? We're not worried about that. We're worried about, can we get the pure product out? And the final concept we'll talk about before we stop is an azeotrope. And these guys are the troublesome guys. Looking at this diagram back here, it's really nice. We can keep going the lever roll, and keep going down. Like you're sliding down a slide. You're going to keep going down the steps. It's easier and easier until we get to one side or the other. Well, not everything works that way. Because this assumes ideality, that the A to A interactions and A to B interactions and the B to B forces are all equivalent. But in a real solution, there's going to be a point where the A and B forces are either going to be greater than the A to A and B to B, or they're going to be less than the A to A and B to B, because the B to B and A to A are not the same. So we're going to have a different bottom point. Essentially, we can lead to either a maximum or a minimum boiling azeotrope. So where the endpoint is not at the extrema. So right here, separating a real mixture, we can't always reach. We're always going to try to reach a minima, but you may not be able to go one way or the other. So depending on where we're at and which diagram we're dealing with depends on what's the best thing you can do. On this guy, if you're on this side, you cannot separate these two. But if you're on this side of this, you can purify the initial X. At high concentrations, you can get an even higher concentration. But below that, you cannot get it any higher. This guy, you cannot ever fully purify it. You're going to essentially get more and more pure until we hit this minimum, and then they're both going to boil out together. You're not going to get any more pure. So the maximum boiling fractional distillation can recover pure A, starting to the right of the max. But the rest is the special type of inseparable mixture we call it azeotrope. So that these azeotropes, the further boiling of this gives a constant composition of this mixture that's not going to separate at all. Now, when we get a minimal boiling, the distillation leads to a concentration of purity in what isn't vaporized. So whatever is not being vaporized becomes pure, but everything else, the vapor, you can't get the vapor out. The vapor is garbage. In this case, you can get like the pure vapor eventually. In this case, you can get pure liquid. But so this is a problem like oftentimes like when you're like rotoevaporating something, you might use water. Well, you might use a certain compound in there to azeotrope the water out. You mix in this in, and then you boil it. It's a little bit easier to boil, and it makes sure you get all the remaining water out. Okay, so that's where we're going to stop for now, and we'll talk more about this later.